Hello everybody, my name is Lukas Malay and I would like to present my work on Summer of HPC project. Some basic information about project for beginning. The project name is Parallel K-means Clustering in Computational Astrophysics, and I spent almost 2 months working on that project at Niels Bohr Institute in this nice old building in Copenhagen in Denmark. And work on this project was collaboration with another Summer of HPC student with Moti. So let's focus on the project and put some questions. What does it mean K-mean clustering in astrophysics? What astrophysical project is it? What is it K-mean clustering and why we need it? And why parallel K-means? That's a lot of questions for beginning, but don't worry, I have some answers. The project is connected with astrophysical plasma simulation, where a large number of particles is used to simulate plasma behavior. You can see figure which shows particle simulated plasma, and the particles are in 6 dimensions, 3 position coordinates and 3 momentum coordinates. During plasma simulation, the number of particles increases exponentially in consequence of particle collisions, where new particles with smaller mass are created. And this growth of particles leads to overflow in memory consumptions. To control particle growth and also to keep physical correctness of simulation, we can use K-mean clustering method to merge close particles together. We can show an example on figure. As first, we have some particles in space. Next, we find clusters of particles. Here, for example, we want only 2 clusters, so we have red cluster and blue cluster. And finally, for each cluster, we merge particles together into one new particle with larger mass. So this is exactly what K-means clustering does. But unfortunately, this clustering process with naive brute force algorithm takes 20 minutes for simulation, which takes only 2 minutes. And that's the reason why we need to do it in parallel, or at least somehow better. There are 2 basic approaches how to do K-means. The first one, brute force algorithm, that is the original algorithm which was used in Plasma project. This algorithm is simple and it is possible to implement it using massive parallelization. That is what we did. So we implemented this brute force algorithm on GPU and got speed up 1000 against the same sequential algorithm. Next approach is algorithm using KD tree structure, what is data structure for partitioning points in space. This algorithm distinctively decreases computation of distances and is much more faster than brute force algorithm, but is more complex and it is quite tricky to parallelize it. However, to reach the best performance for this algorithm, we vectorized computation of distances using simmed vectorization with SSE AVX instructions. And next, we also implemented OpenMP parallelization, where we used OMP tasks for tree traversing. At the end, some graphs to demonstrate our results. We tested our implementations on case which is typical for large plasma simulation, where we want to reduce 2.4 million particles into 2 million. Here we can see results for original implementation compared with GPU implementation of brute force algorithm and CPU multithread implementations of KD tree. The speedup against original algorithm is about 1000 for GPU and also for KD tree. When we zoom in to see something more, we can see that the KD tree algorithm is really very fast, even in sequential case for one thread. And next, it is great scalable up to 64 threads. 64 threads was the optimal value, and for more threads we didn't get any extra speedup. In any case, for both parallel implementations, we reached great results and made from 20 minutes only a few seconds. And that's all. Thank you for your attention.